So after everything that we've talked, we can finally, I hope, make sense of pulmonary ventilation. How do we actually get air in and out of our lungs on a functional level? So what we will start with is inhalation, breathing air into the lungs. How is this accomplished? Anytime that you want to breathe air into your lungs, right? You want to inhale air into your lungs. What happens is a combination of two things. The external intercostal muscles will contract. These are skeletal muscles. Okay? The external intercostal muscles will contract, and the diaphragm will contract. To begin the process of breathing in air, inhaling air, this is the first thing that happens. Your external intercostal muscles and your diaphragm muscle will contract. If your external intercostal muscles contract, you know what that will do based upon previous lectures. It will cause the ribs to move up and out, okay? Like lifting the handle on a bucket, right? When the external intercostal muscles contract, the ribs move up and out. There's a very easy way to prove this. Take a breath in and feel what happens to your ribs as you do that. Put your hands on your ribs and then take a breath in. Inhale. What you'll feel as you are beginning to inhale, what will happen is your ribs will move up and out as you are breathing in. And that is because of the fact that your external intercostal muscles are contracting. That's causing the ribs to move up and out. What's the relevance of this? Well, we're going to talk about that in just a minute. This I'm going to focus on less because you can't see this happening, for one thing, which makes it harder, visually to understand, but I'll mention it nonetheless. When you inhale, your diaphragm also contracts, okay? And what happens is the diaphragm, when it contracts, the central tendon moves downward towards the lower border, lower borders of the lowest ribs and towards the lumbar vertebrae, and it causes the diaphragm to flatten out. The diaphragm is actually the more important muscle for what's called quiet breathing, like the standard type of breathing that we do, but it's also more difficult to realize what it does conceptually. Since you can see the ribs move up and out as you're breathing, it's easier, in my opinion, to visualize what happens on that level compared to what happens on the level of the diaphragm. So we're going to focus less on the diaphragm, but I am nonetheless pointing out to you that when you breathe in, the diaphragm contracts and it flattens out. That's the other thing that is going to be happening. If when we inhale, the ribs move up and out, what is the relevance of this? Okay. And we'll talk about the diaphragm too, but we're going to focus on the ribs. So when we inhale, the external intercostal muscles contract, and the ribs move up and out. What effect is this going to have? Okay, what's attached to the inside of the chest wall? What's attached to the inside of the chest wall, as we have spoken about in so much detail, is what's called the parietal pleura. The outer layer, the outer portion of that deflated sac that is the pleural membrane. The portion of the pleural membrane that does not make contact, direct contact, with the lung itself, and instead actually adheres to the inside of the chest wall. Okay, well, what's the chest wall doing right now? The chest wall, which is made up mostly of the ribs and the external intercostal muscles, the chest wall is moving up and out as you're breathing in? Well, if the parietal pleura is attached to the inside of the chest wall and the chest wall is moving up and out, clearly that's going to be pulling the parietal pleura up and out because the parietal pleura is attached to the inside of the chest wall. Look over here. This is the parietal pleura. I'm highlighting more than just the parietal pleura, but I'm trying to make a point here. There's the parietal pleura attaching to the inside of the chest wall. Well, when you're breathing in, inhaling, the chest wall, the ribs, along with the external intercostal muscles, right, they move up and out. And that pulls the parietal pleura up and out. Because the parietal pleura attaches to the inside of the chest wall, and the chest wall is moving up and out. Here is another way to visualize this. The chest wall is moving up and out. What's attached to the inside of the chest wall? Well, right here, it's the parietal pleura. And if the chest wall is moving up and out, then the parietal pleura, which attaches to the inside of the chest wall, is also moving up and out. I know I just said this, but it's just a different image, so I'm trying to provide some more imagery here of what's happening so that you can hopefully visualize this a little bit better. This I'm going to focus on less. I'm going to leave this part kind of up to your imagination after stating one thing. When the diaphragm contracts, the diaphragm flattens out. What's attached to the upper side of the diaphragm? Well, the parietal pleura, right? That exists around or encompasses around the base of the lung. Okay, so the parietal pleura is attached to the diaphragm. And if during inhalation, when we're breathing air into our lungs, inhaling air, if during this process, to begin this process, the diaphragm contracts and it flattens out, if the diaphragm flattens out and the parietal pleura, kind of around the base of the lung, is attached to the diaphragm, then the parietal pleura will flatten out. Another way of saying that is the parietal pleura will be pulled away from the lung, or even better yet, pulled away from the visceral pleura, which is what we need to talk about now. For the remainder of this lecture, I'm going to focus on the chest wall and the external intercostal muscles. But you can imagine everything that I'm about to talk about with relationship to the chest wall and the parietal pleura that attaches to the inside of the chest wall. All of these concepts are going to apply exactly in exactly the same way that they do to the diaphragm. Because the chest wall moving up and out due to the external intercostal muscles and the diaphragm flattening results in ultimately the same thing, just in different directions. The chest wall moving up and out pulls the parietal pleura up and out, and the diaphragm flattening out pulls the parietal pleura downward. Okay, you'll know what I'm talking about in just a minute, but I just want to be clear. I don't have the time, nor do I want to dedicate the time to focusing on the diaphragm any more than just saying this. So let's get back to focusing on the external intercostal muscles. When you breathe in, the external intercostal muscles will begin to contract. That's the first thing that happens when you begin the process of inhaling. The external intercostal muscles contract, and that causes the ribs, the chest wall, to move up and out, like the handle on a bucket. If I've said this now multiple times, but since I went off on a tangent about the diaphragm, I want to readdress what happens. If the chest wall moves up and out, what's attached to the inside of the chest wall? Well, the parietal pleura is. So if the chest wall moves up and out, that means the parietal pleura is pulled up and out. If the parietal pleura is pulled up and out due to the chest wall moving up and out, then what's happening with regard to the whole pleural cavity? That's the question that ultimately has to be asked here. And the answer is, if during inhalation, the chest wall moves up and out and it pulls the parietal pleura up and out, what it's really doing is it's pulling the parietal pleura further away from the visceral pleura. The two are being further pulled away from one another because the chest wall is moving up and out. Again, I can draw it over here too. The chest wall is moving up and out, and that's pulling the entire parietal pleura, which attaches to the entire inside of the chest wall. That's pulling the entire parietal pleura up and out and away from the visceral pleura that attaches to the lung. Now you think, well, what is that going to translate into? Well, if we're inhaling and the chest wall is moving up and out, pulling the parietal pleura up and out, and pulling the parietal pleura further away from the visceral pleura, what's going to happen is the volume of the of the pleural cavity is going to expand, right? That's the point here, is if you pull the parietal pleura further away from the visceral pleura, then the pleural cavity, right, the volume of it will expand. So let me be as clear as possible here. The purpose of the chest wall moving up and out when you inhale is to actually pull the parietal pleura, which attaches to the inside of it, away from the visceral pleura, which attaches to the lung. And by pulling that parietal pleura further away from the visceral pleura as the chest wall moves up and out, you expand the volume of the pleural cavity. And here is now the big point. What will that do? If you expand the volume of the pleural cavity, what is that going to do to intrapleural pressure? It's, of course, going to decrease it. Okay? It'll decrease it on average throughout the entire pleural cavity. It varies actually. When you get into more advanced respiratory physiology, you see that the degree to which it changes is very different from the bottom to the top of the lung. But on average, it decreases it by somewhere approximating 2 millimeters of mercury. So it'll drop from like 756 down to, again, this will vary from one text to the next, but like 754 about. And you say, well, why is it dropping? Because what are you doing? When you're inhaling and the chest wall is moving up and out and it's pulling the parietal pleura further away from the visceral pleura, it's causing the pleural cavity to expand. And if the pleural cavity expands, we'll pretend that there's air in here, then the air has more room to kind of float around, even though we know it's fluid, but it has more room to float around, and the gas molecules wouldn't be as tightly compacted, and that would drive the pressure down. Intrapleural pressure is going to fall here. So a perhaps simpler way of saying this, although I would ask for more detail on an exam, is that when we inhale, intrapleural pressure falls. When we inhale, the volume of the pleural cavity increases, which drives down intrapleural pressure. And now, of course, the next question is, why would we want to drive down intrapleural pressure? To answer that question, you have to think about, has anything happened to intra-alveolar pressure yet? The air pressure within the lungs? No, it's still 760. The air pressure in the lungs is still 760, while the air pressure in the pleural cavity has fallen from 756 down to 754. So what does that actually imply? And this is where that concept that we finished with, that value, I should say, that we finished with at the end of the last lecture becomes important. What is transpulmonary pressure? Transpulmonary pressure is the difference between intra-alveolar pressure and intrapleural pressure. To start off with, it was 4, technically -4 millimeters of mercury. Okay, 760 minus 756 to start off with, minus 756 to start off with is 4. Again, it's always a negative value, so it would be called -4. Okay, now what has happened? When we have begun the process of inhaling, the chest wall moves up and out, pulling the parietal and visceral pleura further away, expanding the volume of the pleural cavity, driving down intrapleural pressure another 2 millimeters of mercury to 754. So 760 minus 754 is what? 6 or -6. Now, what's the point? What does that even mean? It means that there is a bigger pressure gradient. There's a bigger pressure gradient between the air in the lungs, right? Intra-alveolar pressure, the air pressure in the lungs, and the air in the pleural cavity, air pressure within the pleural cavity. Now the gradient is 6 or -6 millimeters of mercury rather than 4. Intra-alveolar pressure is 760 and intrapleural pressure is 754. So now there is a 6 millimeter of mercury, -6 millimeter of mercury pressure gradient between the air in the lungs and the air in the pleural cavity. That means the air in the lungs will want to expand outwards towards the pleural cavity much more forcefully, right? Because you have significantly increased the pressure gradient from 4 to 6. That's technically a huge increase in the pressure gradient between, just as a percentage, it's a huge increase in the pressure gradient between the air in the lungs and the air in the pleural cavity. So what you have to understand is now the air in the lungs wants to expand outwards towards the air, which again is technically fluid, but air in the pleural cavity much more forcefully. And of course, this is going to be happening right on both sides. The intra-alveolar pressure is still 760 within the lungs. In the pleural cavity, approximately, it's 754, which is an increase. It's an increase in transpulmonary pressure because it went from 4 to 6 or -4 to -6. It's an increase in transpulmonary pressure. So now the air in the lungs wants to expand outwards towards the pleural cavity much more forcefully. Intra-alveolar pressure, the air pressure within the lungs, is now even greater than intrapleural pressure. It's even greater than it used to be. The technically air pressure within the pleural cavity. So the air wants to expand from the lungs out towards the pleural cavity more forcefully. And then you think, well, what effect does this have on the lungs? The answer is that it causes the lungs to expand. As you can see in this image, what has happened, right? The lungs, when we inhale, expand within the thoracic cavity. Now, in something like anatomy, where you don't have a lot of time to talk about the physiology of this, why the lungs expand when we inhale should actually inherently seem incredibly simple. You think, well, okay, when we inhale, the chest wall moves up and out. That kind of expands the volume of the thoracic cavity and pulls the lungs outwards, and then that causes the lungs to expand. But that's not what causes the lungs to expand at all. It's not nearly that simple. What actually causes the lungs to expand when we inhale is, yes, the chest wall moves up and out. But as the chest wall moves up and out, the purpose of that is to actually expand the volume of the pleural cavity. And by expanding the volume of the pleural cavity, what do? You drive down intrapleural pressure from an average of like 756 down to 754, all while the air pressure in the lungs, intra-alveolar pressure, stays at 760. So what have you accomplished here? You have increased transpulmonary pressure. And now the air in the lungs want to expand out towards the pleural cavity much more forcefully, right? There's a bigger pressure gradient between the air in the lungs, intra-alveolar pressure, and the quote-unquote air within the pleural cavity, intrapleural pressure. So because of that bigger gradient, 6 rather than 4, -6 rather than -4, the air in the lungs wants to expand outwards towards the pleural cavity much more forcefully, and that actually then causes the whole lung, both of them, to expand within the thoracic cavity. The increase in transpulmonary pressure, as it's called, is what actually physically allows for the lungs to expand in the thoracic cavity. And we think that it's all related to the fact that the air in the lungs wants to expand outwards, move outwards towards the pleural cavity much more forcefully when you drive down intrapleural pressure and thus increase transpulmonary pressure. And then this causes the lungs to actually expand. But that leads into a whole separate conversation, which is, well, now I know why the lungs expand when we inhale, but what's the purpose? Like, what's the function of causing the lungs to expand? Why do we want that to actually happen? Maybe I know why it happens. It happens due to this increase in transpulmonary pressure. But what's the explanation for why we want this to happen? I'm going to draw you a very simplified image here. Here is one alveolus. Here is the pleural cavity on the left and right side. All right, to begin, intrapleural pressure is 756. Intra-alveolar pressure, the air pressure in the alveoli, and thus the lungs, is 760. Now, you inhale, and when you inhale, the chest wall moves up and out. If the chest wall moves up and out, that pulls the parietal pleura further away from the visceral pleura and decreases intrapleural pressure to 754. Okay? Nothing has happened yet to intra-alveolar pressure. The air pressure in the lungs is still 760. So now transpulmonary pressure has gone from -4 to -6. So the air in the lungs, the air in the alveoli, wants to expand outwards much more forcefully, right? There's a big increase in the pressure gradient, transpulmonary pressure here. So the air in the lungs, the air in the alveoli wants to expand outwards much more forcefully. And what that does is it causes the lungs to expand. And more importantly, it causes the alveoli to expand. Because where's the air actually located? The air is located mostly in the alveoli. And what happens is the air in the alveoli wants to expand outwards more forcefully due to this increase in the gradient, transpulmonary pressure, and then that causes the alveoli themselves, which again make up most of the lungs, to expand. And what will happen here is intra-alveolar pressure will fall, right? Because if the alveoli, the lungs, expand, then the volume inside of this one alveolus here is going to become larger. The volume of the alveolus is larger, so now there's more room inside of this alveolus for the gas molecules that make up the air to float around, and that's going to drive down the air pressure in the alveoli. Intra-alveolar pressure will fall from like 760 to like 758 or so. This is fundamental. Like, you need these alveoli to expand because you want intra-alveolar pressure to fall. If you increase the volume of the alveoli by causing them to expand, which is all happening due to this increase in transpulmonary pressure, by the way, then through the expansion of the alveoli in terms of volume, you drive down intra-alveolar pressure, in our example by about 2 millimeters of mercury. Okay, but what about atmospheric pressure? Atmospheric pressure is still 760. So now where is there a pressure gradient? Now the air pressure in the lungs, the air pressure in the alveoli, is less than the air pressure in the atmosphere. Another way of saying that is intra-alveolar pressure, the air pressure in the alveoli, is now less than atmospheric pressure, the air pressure in the atmosphere. So what's going to happen here? Air now is going to move from the atmosphere into the lungs. Air always moves from high pressures to low pressures, and by expanding the alveoli and driving down intra-alveolar pressure, you've created a pressure gradient between the air in the atmosphere and the air in the alveoli. The air pressure in the atmosphere is higher than the air pressure in the alveoli. Intra-alveolar pressure is less than atmospheric pressure, which is greater. Air is going to move from high pressures to low pressure, so air is going to move from the atmosphere into the lungs. This is how we get air into our lungs. This is how we actually inhale. This is the process. And this is also why the air that comes in through your mouth into your pharynx moves down and through the glottis into the larynx and the trachea rather than the esophagus, because there's a pressure gradient pulling the air in that direction. So this is the first step of the process of pulmonary ventilation. It's understanding how air gets from the atmosphere into the lungs. And I think most people, they would never imagine that it would take 3 hours of lecturing and videos to make complete sense of it. But I think it does, because it is far, far more complicated, as I tried to say at the beginning, than anyone would ever think. So let's do it by looking at this image. When you begin to inhale, the external intercostal muscles contract, pulling the chest wall up and out. That pulls the parietal pleura, which attaches to the inside of the chest wall, further away from the visceral pleura, which attaches to the lung. By pulling the parietal and visceral pleura further away from each other by the chest wall moving up and out, thanks to the contraction of the external intercostal muscles, that expands the volume of the pleural cavity, driving down intrapleural pressure, right? From 756 to 754, right? The volume of the pleural cavity has increased, so intrapleural pressure falls to 754, all while intra-alveolar pressure stays exactly the same. So what have we gotten here? We've gotten an increase in transpulmonary pressure. The pressure gradient between the air in the lungs and the air in the pleural cavity. So now, due to this increase in transpulmonary pressure, the pressure gradient, 760 versus 754, the air in the lungs, really the alveoli, wants to expand outwards towards the pleural cavity more forcefully. What does that do? It causes the lungs to expand, particularly the alveoli. And as the lungs and the alveoli expand, that increases the volume of the lungs, increases the volume of the alveoli, and that drives down the air pressure in the lungs. That drives down intra-alveolar pressure from 760, in my example, to 758. Okay, well, atmospheric pressure is still 760. That hasn't changed. So now the air pressure in the atmosphere is greater than the air pressure in the lungs because the lungs have expanded. The volume has increased, driving down the air pressure in the lungs. So since the air pressure is greater in the atmosphere than it is in the lungs, what's going to happen is air is going to move from the atmosphere into the lungs. So now you should be able to understand the first part of this graph, okay, which can be quite confusing. So you see between 0 and 2, and then 0 and -6, that's all in reference to atmospheric pressure, which we know is 760. So if it's at 0, that means that it's equal to atmospheric pressure, which is 760. Let's say it's at -6. That would mean that it's equal to 6 millimeters of mercury less than atmospheric pressure, which would be 754. Okay, so what this is actually showing you is two different lines. This line here is intra-alveolar pressure. This line here is intrapleural pressure. So this is the beginning of inspiration. Well, let's say before inspiration has even started. Intra-alveolar pressure is 760, which is the same as atmospheric pressure. So since intra-alveolar pressure and atmospheric pressure are the same, intra-alveolar pressure starts off right here at 0. Now, what do we know about intrapleural pressure? It's about 4 millimeters of mercury less to start off with than atmospheric pressure or intra-alveolar pressure. Point being, intrapleural pressure is about 756. 4 millimeters of mercury less than atmospheric pressure, and 4 millimeters of mercury less than intra-alveolar pressure to start off with, right? That's why the purple line, which denotes intra-alveolar pressure, is at -4, because it starts off 4 millimeters of mercury less than atmospheric pressure. So it's at 756. Okay, that's where that comes from to start off with. Now, what happens when we begin to inhale? When we begin to inhale, the chest wall moves up and out. As the chest wall moves up and out, what does that do? It expands the volume of the pleural cavity. If the chest wall moves up and out, and that pulls the parietal and visceral pleura further away from one another, then that expands the volume of the pleural cavity and drives down intrapleural pressure. And you can see that's what's happening here. Intrapleural pressure is falling. And that's what happens during inspiration, is intrapleural pressure falls. Why? Because the pleural cavity expands when we inhale, because the chest wall moves up and out and pulls the parietal and visceral pleura further away from each other, expanding the volume of the pleural cavity and driving down intrapleural pressure. That is why the purple line begins to decrease, become more negative, when inspiration is occurring. And what does it show you? It shows you that intrapleural pressure falls to about, it goes down about 2 more millimeters of mercury, approximately. It goes from 756 to about 754. It's going to vary a little bit from textbook to textbook, but intrapleural pressure is going to fall about 2 millimeters of mercury or so. So now intrapleural pressure is 754. What does that mean for transpulmonary pressure? Intra-alveolar pressure, the air pressure in the lungs, has stayed approximately the same. So that's caused an increase in transpulmonary pressure. And now the air in the lungs, the air in the alveoli, wants to expand outwards more forcefully, and it does, and that actually causes then the lungs and thus the alveoli to expand. And when the lungs and thus the alveoli expand due to this increase in transpulmonary pressure, that causes a decrease in intra-alveolar pressure, the air pressure in the lungs. Since the lungs and thus the alveoli have expanded, there's more room for the gas molecules that make up the air to float around. They're less compacted, and thus air pressure in the lungs decreases due to this increase in volume. Another way of saying that, intra-alveolar pressure decreases from 760. I gave you an example of about to 758, although this image is a little bit more conservative, and it only goes down by about 1 rather than 2, but that makes absolutely no difference. What the image is showing you is that there's a clear decrease in intra-alveolar pressure, right? Intra-alveolar pressure decreases when we inhale, and that's thanks to the fact that the lungs expand, the alveoli expand, which drives down intra-alveolar pressure. Now you'll notice the one confusing part of this is inhalation doesn't end until right here. And what you'll notice is that intra-alveolar pressure, I'll draw it in red, actually begins to increase during the second half of inspiration. Why would intra-alveolar pressure begin to increase during the second half of inspiration? Meaning once inspiration has come to an end, like this, again, I'll draw it in red. Again, that's when inspiration has come to an end, but I just drew in red there, that line. When inspiration has come to an end, you'll notice that intra-alveolar pressure is back to about 760. So during the second half of inspiration, intra-alveolar pressure rises until it's actually back to 760 at the end of inspiration. How could that be? And the answer is quite simple, actually. Well, because what's happening during the second half of inspiration? During the second half of inspiration, air is actually coming from the atmosphere into your lungs and into the alveoli. Starting about, let's draw it, I don't care, in green. Starting about right here, this is the point at which air actually is now coming from the atmosphere into the lungs. Atmospheric pressure is 760, while intra-alveolar pressure is, in my example, 758, in their example, 759, whatever the case might be. This is causing air from the atmosphere to move into the lungs due to this pressure gradient. And as air is coming from the atmosphere into the lungs, what's happening? More and more air is filling in the lungs, in the alveoli. More and more air is getting packed into these alveoli. And now, as more and more air actually comes into these alveoli, the gas molecules are more compacted, surrounded around each other, and that drives up intra-alveolar pressure. It drives up the air pressure in the lungs. The air pressure in the lungs increases during the second half of inspiration, and intra-alveolar pressure will continue to increase during the second half of inspiration until it equilibrates with atmospheric pressure. So at the end of inspiration, intra-alveolar pressure will actually rise back up to 760, which is exactly the same as atmospheric pressure, which is 760. And that part sounds maybe a little bit confusing, but it's not that bad. Just think about it. This, this graph, I actually understand completely why it throws people off, but conceptually, if you work through it, what I'm trying to say is it's not that bad. Like, the first half makes sense to most people from my experience. Not everybody, but most people. You say, okay, when we inhale, intra-alveolar pressure falls. Okay, I'll draw that in red right here. Intra-alveolar pressure during the first half of inspiration falls. And it's like, well, that makes perfect sense because when we inhale, the lungs expand. Okay? And the alveoli expand. And that drives down intra-alveolar pressure, right? It goes from 760 in my example down to 758. That's what's happening here, right? Intra-alveolar pressure during the first half of inspiration is falling. It's decreasing. That's due to the expansion of the lungs and thus the increased volume of the lungs and the alveoli, which is driving down intra-alveolar pressure, right? There you can see it. But then all of a sudden, we can do it again in black, during the second half of inspiration, intra-alveolar pressure, the air pressure in the lungs and the alveoli, it begins to rise. And you think, why is that? And it's like, well, because what happens during the second half of inspiration, starting right here, is air is moving from the atmosphere into the lungs. It's moving down its pressure gradient. Atmospheric air is moving into the lungs, right? Because atmospheric air pressure is greater than intra-alveolar pressure, and air is moving from the atmosphere into the lungs. And that air, and thus gas molecules that make up the air, are packing inside of these expanded alveoli. And as more and more air and gas molecules that make up the air pack inside of the alveoli, that drives up the air pressure in the expanded alveoli. If you pack more air in there, then the air pressure within the alveoli just goes right back up. And that's what causes the rise in intra-alveolar pressure during the second half of inspiration. It's the fact that air is coming from the atmosphere into the lungs and then packing inside of these alveoli and driving up the air pressure in the alveoli. The gas molecules, since there's more in here now coming from the atmosphere, right? These gas molecules are now more tightly compacted, and that's driving up the air pressure. And this will continue to happen until intra-alveolar pressure and atmospheric pressure equilibrate, right? They become exactly the same. And then there won't be a gradient anymore. So that's why you get stuck right here at the end of inspiration. Atmospheric pressure and intra-alveolar pressure become identical again at the end of inspiration. And then you say, well, what about intrapleural pressure? Well, intrapleural pressure is still 754. That hasn't changed at all, right? Because air hasn't traveled into the pleural cavities. Once inspiration has happened, the parietal and visceral pleura are pulled apart, increasing the volume of the pleural cavity, which has driven down intrapleural pressure to 754, and that's still exactly the same. So at the end of inspiration, at the very end of inhaling, intra-alveolar pressure is 760, and intrapleural pressure is still 754. And now we begin the process of discussing expiration. How do we get this air that's in the lungs back out into the atmosphere? What will happen when we exhale? To begin the process of exhaling is usually a very passive process. It's not like when we're exercising, it can become very active, but generally as we're breathing throughout the course of the day, the process of exhaling is very passive. What that means is to exhale, we don't typically contract muscles. All we do is we relax the inspiratory muscles. Let me say that a little differently. When expiration begins, what happens is the external intercostal muscles relax. They stop contracting. And when the external intercostal muscles relax and they stop contracting, what happens is the chest wall begins to fall back down and inward. And the same thing happens with the diaphragm. When we exhale, the diaphragm relaxes and it starts to balloon back upwards. Okay. Again, we're not focused on the diaphragm, we're focused on the external intercostal muscles, but I wanted to point that out nonetheless. The big thing here is when we begin the process of exhaling, the external intercostal muscles relax. And now, if the external intercostal muscles relax, there's nothing pulling the ribs up and out anymore. So what will happen to the ribs is they'll begin to fall. The ribs will begin to fall down and inward. Another way of saying that is the chest wall begins to fall down and inward when we exhale. If you don't believe me, just test out the theory. When you exhale, feel what happens to your chest wall, to your ribs. When you exhale air, your rib cage, your ribs, excuse me, your chest wall, it'll begin to fall down and inward. And then you would think, well, what effect is that going to have? Well, if during expiration, the chest wall begins to fall downward, right? Down and inward. Because of the relaxation of the external intercostal muscles, the chest wall begins to fall down and inward. What is that going to do to the parietal pleura, which attaches to the inside of the chest wall? The answer is, well, if the chest wall falls downward and inward, and the parietal pleura is attached to the inside of the chest wall, then the parietal pleura will begin to fall down and inward. And what I'm saying here actually is, as the chest wall begins to fall down and inward, and the parietal pleura, which is attached to the inside of the chest wall, begins to fall down and inward, that means that the parietal pleura and visceral pleura will get closer together. The volume of the pleural cavity will decrease during expiration. Why is this volume of the pleural cavity decreasing? Well, because the parietal and visceral pleura are moving closer together during the process of exhaling. Right? The chest wall, when we begin to exhale, falls down and inward, pushing the parietal and visceral pleura, closer together, decreasing the volume of the pleural cavity. And what's that going to do to intrapleural pressure? The pressure, air pressure, which is actually fluid, but the air pressure within the pleural cavity. If you decrease the volume of the pleural cavity, then the gas molecules, which is really water, are going to be more tightly compacted, and intrapleural pressure will rise. When we begin to exhale, intrapleural pressure increases because the visceral and parietal pleura move closer together. It goes back from like 754 back to what it is at rest, which is 756. When we exhale, intrapleural pressure rises due to the volume of the pleural cavity decreasing from the parietal and visceral pleura moving closer together. All right, now what we have to think about, what does that actually mean? Well, if intrapleural pressure has now risen back up to 756, what is the air pressure inside of the lungs? The air pressure inside of the lungs is 760. At the end of inspiration, the air pressure in the lungs is 760, and we can presume that it's still 760. Intra-alveolar pressure is 760, while intrapleural pressure is 756. So what has happened here? Transpulmonary pressure has actually decreased, because at the end of inspiration, what is intrapleural pressure? It's 754. Well, intra-alveolar pressure is 760. So that's a transpulmonary pressure of -6. Then when we begin the process of exhaling, the chest wall falls down and inward, pushing the parietal and visceral pleura closer together, decreasing the volume of the pleural cavity, driving up intrapleural pressure to 756. Now what is transpulmonary pressure? Transpulmonary pressure has decreased from 6 or -6 to 4 or -4. There's not as strong of a pressure gradient between the air in the alveoli and the air in the pleural cavity. So what is that going to mean? And I'll draw you a different image to explain this. All right, so this is the end of inspiration. Intra-alveolar pressure is 760, the same as atmospheric pressure. Intrapleural pressure is 754. So transpulmonary pressure is 6 or -6. Okay. Then we begin the process of exhaling. The chest wall moves down and inward, bringing the visceral and parietal pleura closer together. If the visceral and parietal pleura get closer together, that decreases the volume of the pleural cavity, and that increases intrapleural pressure from 754 to 756. What has that done to transpulmonary pressure? Right? It went from -6 to -4, so we would say that transpulmonary pressure during expiration, the process of exhaling, decreases. Okay, now there's not as big of a gradient for the air within the lungs, within the alveoli, to expand outwards towards the pleural cavity. And mind you, this is something you can't forget. These alveoli are very enlarged compared to what they normally are at rest, and they're packed with a whole bunch of air that came in from the atmosphere. So again, this is the end of inspiration and the beginning of expiration. The alveoli are very large, right? They're heavily expanded, and they're packed with air that came in from the atmosphere. Okay, now all of a sudden, transpulmonary pressure decreases because intrapleural pressure increases, right? It went from 754 to 756 due to the shrinking of the pleural cavity, decreasing in volume. So now the gradient for air to travel outwards from the, let's say the air to travel outwards that exists inside of the alveoli. The gradient isn't as strong. Transpulmonary pressure has decreased. The air in the alveoli does not want to expand outwards as forcefully anymore, right? Because now there's only a gradient of 4 rather than a gradient of 6 millimeters of mercury. Transpulmonary pressure has decreased. So again, this air in these very enlarged alveoli, which are heavily expanded, the air doesn't have as strong of a driving force, because the pressure gradient has decreased. It doesn't have as strong of a driving force to expand outwards towards the pleural cavity. And thus what will happen is the alveoli will actually begin to shrink. The alveoli, you can think about it this way, will begin the process of recoiling, right? Like collapsing inward. The lungs, I said this at the beginning, and this is an incredibly important point to this, to this moment. The lungs are incredibly elastic, and they always are looking to collapse inward. Okay? So if you decrease transpulmonary pressure, the gradient for the air in the lungs to expand outwards towards the pleural cavity, which is exactly what has happened here, right? The gradient between the air in the lungs and the pressure gradient between the air in the lungs, the air in the alveoli, and the air in the pleural cavity has decreased. And if you do that, if you decrease that gradient and this air in the lungs isn't as expanding outwards as forcefully anymore. That's going, the force that's keeping these alveoli expanded, that transpulmonary pressure, is going away. It's decreasing. And what will happen is the elasticity of the lungs will take over, and the lungs will start to shrink. They'll start to recoil. They'll start to collapse. The alveoli themselves will start to shrink because you're taking away the transpulmonary pressure, right? You're decreasing it. And now the force that was keeping these alveoli expanded is going away, and the elastic nature, the recoiling nature of the lungs becomes stronger. It takes over, and these alveoli, they begin to collapse. But you have to realize, what are they collapsing around? They're collapsing around a ton of air that came in from the atmosphere, right? So you have these very inflated alveoli that are packed with a ton of air. And now the alveoli are collapsing, right? They're shrinking, they're recoiling around all of this extra air that came in from the atmosphere during inspiration. So if the alveoli are shrinking, they're collapsing inward, the volume of the alveoli of the lungs is decreasing, right? The alveoli are shrinking, they're collapsing, so the volume, the size of these alveoli is decreasing, but it's decreasing around all this extra air that came in from the atmosphere. So what's going to happen to intraalveolar pressure, you think? It's going to go up. It's going to rise to like 762 perhaps, right? Because these alveoli, these very enlarged alveoli, are collapsing around, and they're collapsing around all this extra air that came in from the atmosphere. And now all of this gas, which makes up the air, is becoming very tightly compacted in these alveoli, which are decreasing in volume because they're collapsing. And that drives up intraalveolar pressure, in my example here, to 762. And what's atmospheric pressure? 760. So now all of a sudden, intraalveolar pressure is greater than atmospheric pressure. And what will happen? Air will move from the lungs out into the atmosphere. Why? Because intraalveolar pressure is actually greater than atmospheric pressure. Air moves from high pressures to low pressures. So if air pressure is greater in the lungs, intraalveolar pressure, than it is in the atmosphere, atmospheric pressure, then air will begin to move from the alveoli out into the atmosphere. That is actually how you exhale. And as the air leaves these alveoli out into the atmosphere, what do you think happens to intraalveolar pressure, the air pressure in the alveoli? As the air exits and there's less and less air in the alveoli, intraalveolar pressure will fall because the air is leaving. The gas molecules are leaving and there's less and less in there. And when will it stop? Well, it'll stop at equilibrium. Once intraalveolar pressure hits 760, which is the same as atmospheric pressure, and they're at equilibrium, then it's done. And what have you returned to? You've returned to exactly what you had when we started. The alveoli are shrunken. Intraalveolar pressure is 760, and intrapleural pressure is 756. And now all of a sudden, the process can start over again, and you can begin to inhale once again. Let's look at the graph and do this. So we're right here. This is the end of inspiration. The alveoli are very expanded, and intraalveolar pressure is 760 because a bunch of air from the atmosphere came in and packed inside of these expanded alveoli. Now, to start off with, I have to draw this a little bit to the right here. To start off with, intrapleural pressure is still 754, 754. So transpulmonary pressure is 6 or negative 6. Okay. Now we begin the process of exhaling, expiration. What happens? The external intercostal muscles, they relax. And the chest wall begins to fall down, and inward. As the chest wall falls down and inward, that brings the parietal and visceral pleura closer together. What does that do? It decreases the volume of the pleural cavity. And if you decrease the volume of the pleural cavity, then what are you going to do? You're going to drive up intrapleural pressure. Intrapleural pressure is going to go from 754 back to 756. You see this? When we're exhaling, intrapleural pressure rises, right? It's increasing. And that's because the chest wall is falling down and inward, bringing the parietal and visceral pleura closer together, decreasing the volume of the pleural cavity, thus increasing intrapleural pressure from 754 back to 756. So if you increase intrapleural pressure, then what are you doing to transpulmonary pressure? The difference between intra-alveolar pressure and intrapleural pressure. If you increase intrapleural pressure from 754 to 756, and intra-alveolar pressure stays at 760, then what are you doing? You're decreasing transpulmonary pressure. It's gone from 6 to 4. Okay, so now the driving force, which driving force is always transpulmonary pressure, the difference between intra-alveolar pressure and intrapleural pressure, the driving force has decreased. The gradient has decreased. The air in the alveoli doesn't want to expand outwards as forcefully anymore because there's not as big of a gradient. Transpulmonary pressure. So what happens? The elasticity of the lungs is able to take back over, and the elasticity of the lungs becomes more powerful than the transpulmonary pressure is. And if the elasticity takes back over, then the alveoli, they begin to shrink. And the alveoli shrink around all of this extra air that came in during inspiration. So you have these alveoli collapsing around all of this extra air that came in from the atmosphere. And all that air becomes very tightly compacted. And what does that do? It drives up intra-alveolar pressure. And that's what you see happens during expiration. During the first half of expiration, intra-alveolar pressure rises. And that's because of the fact that the alveoli are shrinking and collapsing around all of this extra air that came in from the atmosphere. Why are the alveoli shrinking in the first place? Well, because there has been a reduction in transpulmonary pressure due to driving up intrapleural pressure. So now there's not as strong of a gradient for the air in the alveoli to want to expand outwards anymore towards the pleural cavity, and the elasticity of the alveoli in the lungs take over, and the lungs begin to collapse. And the alveoli are recoiling and collapsing around all this extra air that came in from the atmosphere, as you can see here, which drives up intra-alveolar pressure, which is what exactly you're seeing here. And it drives it up, in my example, to 762, which is actually greater than atmospheric pressure. So now intra-alveolar pressure is greater than atmospheric pressure. So air moves from high pressure to low pressure. Air is going to move from the lungs out into the atmosphere. That's what happens when you blow air out of your lungs and you exhale. And as the air is leaving the lungs, the alveoli, back off out into the atmosphere, as more and more air is leaving the alveoli is losing air, it's losing gases that make up the air, and thus that decreases the air pressure in the alveoli. As more and more air leaves the lungs, the alveoli, off into the atmosphere, there's less and less air that actually exists in the alveoli itself, and that will cause the pressure to decrease. There'll be less and less gas molecules in here, and they will be less compacted, and thus pressure actually will decrease in the alveoli until it's exactly the same as atmospheric pressure. And that's what you're seeing during the second half of expiration. You're seeing intra-alveolar pressure fall. And that's because the air is actually leaving the alveoli off into the atmosphere. And then at the end of expiration, you have returned to exactly what you had at the beginning of inspiration. Another way of saying that is once you're done exhaling, you are ready to inhale again. This is a cyclical process, just like heart contractions. At the end of expiration, you've returned to exactly the same pressures and lung size and everything else that you had at the beginning of inspiration, because at the end of expiration, you're ready to begin inspiration again. And then the process just repeats itself over and over and over and over again throughout the hours and days and years of your life. And that concludes pulmonary ventilation, the basics of it at least. This concludes the process of how air gets in and out of your lungs. I said this at the beginning, but I'll say it again. Pulmonary ventilation, the process of getting air in and out of the lungs, is no simple process. Most people actually think that it is. It's incredibly complicated and sophisticated, and it uses the manipulation of pressure gradients to get air from the atmosphere in and out of your lungs.